Welcome to today's session. In this video, we'll explore an interesting and thought-provoking problem called bulb switcher. This problem challenges us to reason through a sequence of toggling operations on a set of light bulbs and uncover an elegant solution. Stay tuned as we dive into the details and break it all down step by step. The bulb switcher problem introduces us to a scenario with n bulbs, all starting in the OFF position. The toggling occurs in rounds, each affecting a specific set of bulbs. For instance, in the first round, every bulb is toggled on. In the second round, every second bulb is toggled. This pattern continues, where in the KTH round, every KTH bulb is toggled. The challenge is to determine how many bulbs remain on after all n rounds of toggling. To understand this, we observe that a bulb toggles whenever its position number has a divisor corresponding to the current round. Importantly, a bulb will remain on only if it is toggled an odd number of times. This leads us to the key insight: bulbs at positions that are perfect squares, such as 1, 4, 9, and so on, are toggled an odd number of times because perfect squares have an odd number of divisors. Conversely, non-perfect squares have an even number of divisors, causing those bulbs to return to their initial off state. The realization that only bulbs at perfect square positions remain on simplifies the problem significantly. This means we can reduce the task to counting how many perfect squares exist between 1 and n. One way to approach this is through brute force: simulate the toggling process for all n bulbs and all n rounds. In this approach, we use an array to track the state of each bulb and toggle them repeatedly based on the rules. However, this method requires n squared time complexity, which becomes infeasible for large values of n. Instead, we can leverage the mathematical insight about perfect squares. The number of perfect squares less than or equal to n is simply the integer part of the square root of n. This optimized approach avoids the need to simulate toggling entirely. By directly calculating the floor of sqrt n, we determine the count of bulbs that stay on in constant time, making the solution highly efficient. Given the trade-offs between the brute force and optimized approaches, the optimized mathematical strategy is the clear choice. It takes advantage of the perfect square property to simplify the problem and achieves an time complexity, which is particularly valuable for large inputs. Unlike the brute force method, it does not require maintaining an array to simulate the toggling process, resulting in minimal space usage. While the brute force approach provides a more intuitive understanding of how the toggling works, it is computationally expensive and impractical for large n. The optimized method, on the other hand, provides an elegant and efficient solution by focusing solely on the mathematical properties of perfect squares. The algorithm for this approach is concise: compute the square root of n, take its floor value, and return the result. This represents the count of bulbs that remain on after all rounds. This final piece of the algorithm ties everything together. The function bulbSwitch uses Python's math.sqrt to calculate the square root of n, and then takes the integer part of the result using int. This value directly corresponds to the number of perfect squares less than or equal to n, which is exactly the number of bulbs that remain on after n rounds of toggling. By avoiding unnecessary computations and directly leveraging the mathematical insight, this solution achieves unparalleled efficiency, making it suitable for handling even the largest inputs. With this approach, we've transformed what initially seemed like a complex toggling problem into a straightforward calculation based on fundamental mathematical principles. And that's the beauty of this optimized strategy. To solve this problem, we first need to understand how the toggling process works. Each bulb is toggled in rounds that correspond to its divisors. For example, bulb 1 is toggled in the first round because it only has one divisor, 1. Bulb 6, on the other hand, is toggled in rounds 1, 2, 3, and 6 because its divisors are 1, 2, 3, and 6. The important observation here is that a bulb ends up on if it is toggled an odd number of times. Now, this leads us to a key mathematical insight: only perfect squares have an odd number of divisors. This is because most numbers have divisors that come in pairs, like 1 and 12 or 2 and 6 for the number 12. However, perfect squares like 4 or 9 have one unpaired divisor, which is their square root. For instance, the divisors of 4 are 1, 2, and 4, where 2 is unpaired. As a result, bulbs at positions that are perfect squares will remain on after all n rounds. Finally, to determine how many bulbs remain on, we simply count the number of perfect squares up to n. This is the same as finding the largest integer k such that k squared is less than or equal to n. Mathematically, this is represented as the floor of the square root of n. Now that we have the mathematical insight, let's look at how the algorithm executes. First, we calculate the square root of n using a mathematical function, and then we take the floor of the result to handle non-perfect square values. The integer part of this result gives us the count of bulbs that remain on. This approach drastically reduces the problem's complexity. Instead of simulating all n rounds and toggling each bulb multiple times, a process that would result in n squared time complexity, we leverage the insight about perfect squares to reduce the solution to a simple mathematical calculation, which runs in constant time 1. Additionally, the algorithm is robust enough to handle edge cases. For example, when n is 0, there are no bulbs, so the result is 0. When n is 1, only one bulb is present, and it ends up on because 1 is a perfect square. For large values of n, the algorithm remains efficient due to the simplicity of computing a square root. This solution is highly efficient because it does not require any additional data structures. The entire calculation is based on arithmetic operations, and we don't need arrays or other structures to track the state of each bulb. This minimal use of memory makes the solution optimal for handling large inputs. Let's look at a couple of examples to solidify our understanding. For an input of n equals 10, the perfect squares up to 10 are 1, 4, and 9. This gives us a count of 3 bulbs that remain on, so the output is 3. For another input, say n equals 25, the perfect squares up to 25 are 1, 4, 9, 16, and 25. Here, we count 5 bulbs that remain on, and the output is 5. These examples demonstrate how straightforward the calculation becomes once we understand the relationship between perfect squares and the toggling process. Finally, let's evaluate the complexity of this solution. The time complexity is 1, because the algorithm involves only a constant time computation of the square root and floor operations. This is a significant improvement over a direct simulation approach, which would require iterating through all bulbs and all rounds. The space complexity is also 1, since no additional memory is used beyond a few variables to store intermediate results. This constant space usage, combined with the constant time complexity, makes the algorithm exceptionally efficient, even for very large inputs. This solution to the bulb switcher problem is based on a mathematical observation about the toggling process. The problem involves toggling bulbs and determining how many remain on after n rounds. Each bulb is toggled in rounds corresponding to its divisors. For example, bulb 6 is toggled in rounds 1, 2, 3, and 6. A bulb remains on if toggled an odd number of times. This happens only when the bulb's number is a perfect square, as perfect squares have one unpaired divisor, e.g., 4 has divisors 1, 2, 4, where 2 is unpaired. The number of perfect squares from 1 to n is the integer part of the square root of n, since squaring any integer less than or equal to the square root of n stays within the range. Thus, the problem reduces to computing int, n 0.5, which is implemented in a single line. This solution has 1 time complexity, making it highly efficient. This is the Java implementation of LeetCode problem number 319, bulb switcher. The logic mirrors the Python solution, utilizing the mathematical insight that the number of bulbs that remain on corresponds to the count of perfect squares less than or equal to n. The key difference lies in Java's use of the math.sqrt method for square root calculation and explicit type casting to convert the result to an integer. In the problem bulb switcher, we're tasked with determining how many bulbs remain on after a series of toggling operations on n bulbs. Initially, all bulbs are off, and the bulbs are toggled in consecutive rounds. For example, in the first round, every bulb is toggled on. In the second round, every second bulb is toggled, and in the third round, every third bulb, and so on. By the end of all the rounds, only those bulbs that have been toggled an odd number of times will remain on. Now, the key observation is that a bulb is toggled during rounds corresponding to its divisors. For instance, bulb number 6 is toggled in rounds 1, 2, 3, and 6. Most numbers have an even number of divisors because their divisors come in pairs. However, perfect squares, such as 1, 4, or 9, have an odd number of divisors since one of their divisors is repeated. As a result, only the bulbs at positions that are perfect squares will remain on. So, the solution boils down to counting how many perfect squares are less than or equal to n. Let's explore this with a few examples. When n is 1, there is only one bulb. To determine how many bulbs remain on, we calculate the perfect squares less than or equal to 1. In this case, the only perfect square is 1. This means bulb number 1 will remain on. Why? Because bulb number 1 is toggled exactly once during the first round, making it on. Now, if we consider n equals 10, the calculation becomes slightly more interesting. Here, the perfect squares less than or equal to 10 are 1, 4, 9, corresponding to bulbs number 1, number 4, and number 9. These bulbs remain on after all rounds because they are toggled an odd number of times. For example, bulb number 4 is toggled in rounds 1, 2, and 4, which is 3 times, and bulb number 9 is toggled in rounds 1, 3, and 9, again 3 times. Thus, these 3 bulbs are on at the end. Meanwhile, all other bulbs, such as bulbs number 2, number 3, number 5, and so on, are toggled an even number of times and therefore remain OFF. For instance, bulb number 2 is toggled in rounds 1 and 2, and bulb number 6 is toggled in rounds 1, 2, 3, and 6, both of which are even counts. This confirms that only bulbs corresponding to perfect squares remain on. The output for n equals 10 is 3, as there are 3 such bulbs on. Now, to generalize this, consider that the count of perfect squares less than or equal to n is simply the integer part of the square root of n. This is because the perfect squares are the squares of integers, like 1, 4, 9, and so on. In Python, we can compute this directly using int n0.5, which gives us an efficient way to determine the result in constant time. This insight ensures that we can solve the problem with minimal computation. The solution is highly efficient, with a time complexity of 1, since calculating the square root of n is a constant time operation. Additionally, the space complexity is 1, as we do not use any extra space beyond a few variables for computation. To recap, the essence of the solution lies in identifying that only bulbs at positions corresponding to perfect squares remain on. By calculating the integer square root of n, we directly determine how many such positions exist. This approach is concise, leveraging mathematical properties to deliver an optimal solution to the problem. The time complexity of the solution is 1, which means it operates in constant time regardless of the size of the input. Let's break this down step by step. First, the calculation of the square root of the number, represented as n raised to the power of 0.5, is a mathematical operation that modern systems handle very efficiently. This is because square root calculations are optimized at the hardware or algorithmic level, making this an 1 operation. Second, converting the result of the square root from a floating point number to an integer, which can be done using the int function, is also a constant time operation. Since these are the only operations performed in the solution, and both are 1, the overall time complexity remains 1. No matter how large n gets, these operations take the same amount of time. Now, let's analyze the space complexity, which is also 1. This means the amount of memory used by the solution does not grow with the input size. Here's why: the solution does not rely on any additional data structures, such as arrays or lists. It only uses the input variable, n, and returns a single integer as the output. Furthermore, the intermediate result of the square root calculation, n raised to the power of 0.5, is stored temporarily as a floating point variable. This requires a fixed amount of memory, regardless of the value of n. Since there's no dependency on the size of the input in terms of memory usage, the space complexity is constant, or 1. To appreciate the efficiency of the optimized approach, let's compare it to a naive solution. A brute force method would involve simulating the toggling of bulbs for all n rounds. For each round, you would iterate through up to n bulbs, resulting in a time complexity of n squared. Additionally, this approach would require an array of size n to keep track of each bulb's state, leading to a space complexity of n. In contrast, the optimized solution avoids this by leveraging a mathematical insight: a bulb remains on only if it is toggled an odd number of times, which occurs solely for perfect square indices. By simply counting the perfect squares up to n, which can be done using the square root calculation, the time complexity is reduced to 1. Moreover, no additional data structures are used, ensuring the space complexity remains O1. The mathematical reasoning behind the solution further solidifies its efficiency. The number of bulbs left on corresponds directly to the number of perfect squares less than or equal to n. Why is this the case? A bulb state changes every time it is toggled, and a bulb at position k is toggled once for each of its divisors. Only perfect square numbers have an odd number of divisors, leaving those bulbs on. Mathematically, the number of perfect squares up to n is equal to the largest integer k such that k squared is less than or equal to n. This is calculated as the floor of the square root of n, or int, n 0.5. Since both the square root calculation and the integer conversion are constant time operations, the time complexity is O1. Additionally, the solution does not require any extra memory, so the space complexity is also O1. One common mistake in this problem is misunderstanding how toggling works. Some people assume that all bulbs are toggled the same number of times, but that's not the case. The toggling of a bulb depends on the factors of its position. For example, bulb I gets toggled in rounds where the round number divides I. This means that bulbs with an odd number of divisors, which are perfect squares, are the ones that remain on. Another issue is the brute force approach. Trying to simulate all toggles for every bulb in every round leads to an O(n squared) time complexity, which quickly becomes inefficient for large values like 10 to the power of 6. This approach will time out and is not suitable for larger inputs. Additionally, some confuse the number of bulbs with the number of rounds in the problem. Since the number of bulbs matches the number of rounds, any logic that treats them as separate can lead to errors. Lastly, overcomplicating the math can also be a pitfall. Instead of recognizing the pattern of perfect squares, some try to manually calculate all divisors for each bulb, which is unnecessary and makes the solution more complex than it needs to be. Another frequent issue is off-by-one errors, which occur when forgetting that the bulb indices are 1-based rather than 0-based. This simple oversight can disrupt the toggling logic and produce incorrect results. A key insight to remember is that the number of times a bulb is toggled corresponds to the number of divisors of its index. Only bulbs toggled an odd number of times remain on, and this happens exclusively for indices that are perfect squares, like 1, 4, 9, and so on. Using this insight, the solution boils down to counting how many perfect squares are less than or equal to n, which can be efficiently calculated as floor, sqrt, n. This reduces the problem to an O1 mathematical operation, making brute force simulations unnecessary unless explicitly required in the problem. Variations of this problem might introduce additional rules, such as toggling only specific subsets of bulbs or requiring the final state of all bulbs. For such cases, carefully simulating the toggling with optimizations is crucial. Overall, this problem tests your ability to recognize patterns, particularly around divisors and perfect squares, under the constraints provided. This problem is closely related to other LeetCode problems involving number theory and divisors. For example, LeetCode 319 is the base problem we're discussing, while LeetCode 672 introduces variations with different toggling rules. LeetCode 507, which deals with perfect numbers, and LeetCode 263, focused on ugly numbers, also explore divisor-based patterns. When it comes to solving, there are a few approaches to consider. The brute force simulation method involves toggling each bulb across all rounds, which is straightforward to implement but inefficient with an O(n squared) complexity. This approach is better suited for smaller inputs. On the other hand, the optimal mathematical solution relies on recognizing the perfect square pattern and directly calculating the result as floor, sqrt, n, which is extremely efficient at O1. For variations that require intermediate states or specific subsets, a partial simulation with early stopping can be used. This method balances accuracy and efficiency based on the problem's constraints. Each approach has its trade-offs, but understanding the mathematical insight is key to solving this problem efficiently. Great job! We've covered the bulb switcher problem and explored the elegant mathematical solution. Remember, recognizing patterns like perfect squares can simplify complex problems significantly. Don't forget to practice similar problems to sharpen your reasoning skills. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!